Hello everyone, in this video we're going to review the AP suggested summer packet guided solutions. Number 1. What properties distinguish solids from liquids? Liquids from gases, and solids from gases. Well, liquids can change their shape, or they can flow. Solids, however, cannot. As we know, liquids, when they're in a specific container, will often conform to the shape of their container. So the volume is constant for liquids, it's a definite volume, but the shape is indefinite. So if I transfer water from a beaker to an Erlenmeyer flask, the volume will stay the same amount of space will be occupied. However, how that water looks or how it appears to us would be different. Solids, however, have definite shapes and definite volumes, and no matter where we put that solid, it'll look the same. Gases can undergo large volume changes as pressure changes. Liquids, however, do not. As we know, gases have indefinite volumes and indefinite shapes. So based on the container it's in, it will fully occupy whatever that container is. So if you have a great change in pressure, if you greatly increase the pressure, your volume is going to change as well. If you alleviate the pressure, take less pressure on, it's going to expand. If you do this with liquids, however, that's not the case because they have definite volumes. Gases, like liquids, can flow and they can change volume, as we just discussed. Solids, however, cannot. They have definite shapes and definite volumes. Number 2, how does a heterogeneous mixture differ from a homogeneous mixture? How are they similar? Well, before we get into distinguishing between the two, we have to define what a mixture is. Mixtures are defined as systems containing two or more components that can be separated by physical means. When components mix and blend in such a manner that all of the regions are the same, the system is homogeneous. Some common examples of this that you're familiar with are soft drinks, gasoline, brass, and the air that we breathe. Most mixtures that we see in our real world, though, and in our experience, however, are not homogeneous. Instead, mixtures such as rocks, minerals, river water, blood, fruit salad, pizza, etc., those are all heterogeneous. One way you can determine a homogeneous mixture from a heterogeneous mixture is if you take a sample of that mixture, like if you basically take a portion of it out, does it look the same as the greater mixture? If it does, you have one that's homogeneous. If it looks different, or the components are different, or it doesn't look even, then you have a heterogeneous mixture. These mixtures are similar in that physical methods rather than chemical methods can be used to separate the components. Some examples of these separation methods include filtration, distillation, crystallization, and chromatography. Keep in mind that when you have a pure substance, such as a compound, you could use a chemical method to separate that. Number 3, how does an element differ from a compound? How are they similar? Well, compounds can be broken down by chemical means, whereas elements cannot be decomposed by chemical changes. They are similar in that they both have properties associated with matter. Let's go back to that real quick. So one thing that we can think about, in addition to this, how does an element differ from a compound? Think about what actually makes up an element and what makes up a compound. When you have an element, you're going to have an individual specific type of atom, and that atom is going to have the same number of protons every single time. When you're dealing with a compound, you're dealing with multiple elements combined together. So if you have hydrogen and oxygen, for example, those are basically composed of two different elements, okay, different types of atoms with different numbers of protons. That's another way that we can compare them. Number 4, how do molecules of elements, such as nitrogen, gas, and molecules of compounds, such as water, differ? How are they similar? Well, I kind of just discussed this a little bit. Molecules of elements contain only one type of atom. So if you look at, for example, molecules of elements with N2, we're only really dealing with, two nitrogen atoms being connected together. The atoms have the same number of protons. Whereas if you're dealing with a molecule of a compound, such as water, you're dealing with two or more different types of atoms. So not only do you have a hydrogen atom, which has a unique radius and has a unique number of protons, but you also have oxygen as well. And that, again, has a different number of protons and a different size as well. They are both similar in that they are comprised of two or more atoms chemically bonded together. So for elements, you have two ends connected together, and there's many other examples of this too. For molecules of compounds, you're going to have, again, multiple atoms connected together. The question is, are they the same atom or are they different atoms? Number 5, list the 7 diatomic elements, or molecules, that exist in the natural world. You need to commit these to memory. Often on the AP exam and in class, I might say oxygen gas. I need you to know that oxygen gas is O with a subscript of 2 rather than just O. So here are the 7. We have hydrogen gas, nitrogen gas, oxygen gas, fluorine gas, chlorine gas, liquid bromine, and solid iodine. You'll notice on the periodic table when you look at these, it kind of looks like a number 7 here, which is helpful to remember because there are 7 diatomic elements. Hydrogen is part of the 7, but because of its location, sometimes this is forgotten. Don't forget hydrogen. It's from N to I plus hydrogen, and it looks like a 7. Okay. Now, if you look at how I color-coded these, the gases are in red, the liquid is blue, and the black is solid. This is also on our in-class periodic table on the board. It's important to know that these are these particular states of matter at room temperature. So again, you can adjust, different pressures, different volumes, different temperatures. You can very likely have liquid oxygen. You can have liquid O2. But again, that's under a different set of conditions rather than at room temperature. Number 6, classify each of the following as an element, a compound, or a mixture. Well, the first example is copper. That's going to be an element. Water, if it's pure water, is going to be a compound. However, if it's tap water or bottled water or different things like that often have fortifying agents, or river water or stream water or ocean water, these aren't pure water, right? It's water mixed with other stuff. So we would have a mixture there. Nitrogen is an element. Sulfur is an element. Air is a mixture. Sucrose is a compound. Gasoline is a mixture. Mercury oxide is a compound. Pancake syrup is a mixture. Carbon dioxide is a compound. Let's move on to number 7. Classify the 6 underlined properties in the following paragraph as physical or chemical. So in the first sentence, it says fluorine is a pale yellow gas that reacts with most substances. Describing this particular element as a gas is a physical property because it's the state at which it exists, and indicating that it reacts with most substances indicates a chemical property. Giving that it melts at negative 220 degrees Celsius and it boils at negative 188 degrees Celsius, these are physical properties because they deal with changes in state. Finely divided metals burn in fluorine with a bright flame. Well, when something's undergoing the process of burning or reacting or things like that, that indicates we have a chemical property being observed. And then same thing with the last sentence here. They tell us that 19 grams of fluorine will react with 1 gram of hydrogen. Well, that's a chemical change because we're indicating that different proportions of different elements will react together. Reacting indicates a chemical property. Number 8, convert the following numbers to scientific notation. The first number, we have 24,500. This is a large number, so we would expect a positive exponent. I'm going to move the decimal a certain number of places, either to the left or to the right, until I have a number between 1 and 10. If my decimal point is here at the end of 24,500, I'm going to move it 1, 2, 3, 4 places to the left. So my final answer should be 2.45 times 10 to the 4th power. Again, it's a large number, much bigger than 10, so I'm going to have a positive exponent. 356, that answer would be 3.56 times 10 to the 2nd power. This is a much smaller number than 1, so I'm going to have a negative exponent here. I'm going to move the decimal 4 places to the right to give me 9.85 times 10 to the negative 4th. For letter D, I would move it 1 place to give me 2.22 times 10 to the negative 1. And then for E, I have a large number, again, positive exponent. I'm going to move it 5 places to the left until I have a number between 1 and 10. So I should have 1.22 times 10 to the 5th power. Let's do the reverse of this. Convert the following scientific notation numbers to standard notation numbers. So I'm going to go ahead and move this decimal point 3 places to the right. Again, a positive exponent would indicate a larger number than what I have present. So I'm going to get 4,200. In this case, I have a negative exponent. It should be a number that's smaller than the number we see there. So I'm going to move it 4 places to the left. I would have 0.000215. Same thing, very small number. I would have decimal 5 zeros, 314. For letter D, I have a very large number, so I'm going to move it 5 places to the right. That would be 922,000 would be that answer. Then letter E, I'm moving it 2 places to the right. My final answer should be 957. Number 10, determine the number of significant figures in the following numbers. We have to recognize our zeros are significant or not. So for letter A, the 2, the 5, and the 7 will all be significant. Because this 0 is sandwiched between a 5 and a 7, that is also going to be significant. So I have 4 significant figures there. Letter B, we have to remember that our leading zeros are never significant, or the zeros that come before our first non-zero number. So none of these zeros are significant. Only the 7 and the 7 are significant, so that would be 2 significant figures. Letter C is very similar to letter A in that I have a sandwiched 0. So I have 1, 2, and 4 is significant, and that 0 is also significant. So I would have 4 significant figures. When dealing with scientific notation, you don't want to move the decimal. You want to look at the number at what it's showing you. So I'm only going to look at this 4.7. How many significant figures does 4.7 have? Well, the 4 and the 7 are both significant, so that would have 2 significant figures. For letter E, I notice there is no decimal point present in the number. That means that my trailing zeros, or zeros that come after my last non-zero number, are not going to be significant. So only the 3 and the 4 here are significant. So I should have 2 significant figures there. For letter F, I do have a decimal present, and these zeros are sandwiched. So the 1, the 3, and both zeros are significant, so I have 4 significant figures. Moving on, number 11. Solve the following questions with a calculator and record your answer rounded to the correct number of significant figures. So this is basically calculator work, and then we have to round based on sig figs. So letter A, when you plug that into your calculator, you should get 809.37. Now, if we look at the numbers we're multiplying by, here I have 3 significant figures, here I have 4. When multiplying, you want to select the smallest total number of significant figures. So 3 versus 4 means I have to round this answer to 3 significant figures. So 809 is what I would report. I'm going to check the 4th digit to see if I'm going to round that up or not, or keep it. And it looks like since it's under 5, I'm going to keep it. So my answer should be 809. The next one, I have 123 divided by 3. When I do that, I get the answer of 41. Again, when you're multiplying and dividing, you look at the smallest number of significant figures. So here I have 3 significant figures. Here I have 1. So believe it or not, I have to round this to only 1 significant digit, even though I have just 1 digit there. So it's going to be 40. Again, that 0 is not significant in this number because there is no decimal. If you were to report a decimal, that would be incorrect. Number 6, or letter C. 2.61 times 10, this should be to the negative first power. You're going to multiply that by 356. Again, I have 3 sig figs, 3 sig figs. My final answer should be reported in 3 sig figs. So calculator-wise, it should be 92.916. Round it to 3 sig figs, it should be 92.9. Now, when you add or subtract, the rules are a little bit different. You want to have a number that's as accurate as your least accurate measurement. So I want to report the lowest number of digits, not significant digits, just digits, that come after the decimal. So when I add these two numbers together, I get 67.64, and I look at what comes after the decimal. I have 2 digits here, 2 digits here, so my final answer should have 2 digits as well. Here it's a little bit different. I have a lot of digits after the decimal. Here I only have 1. So when I do my math, you get 12.68887. I'm going to round it so I only have 1 digit after the decimal, because if I compare 6 digits after the decimal to 1, the 1 is the least accurate, so I have to make sure I report it that way. So I'm going to look at the 6, I'm going to check the digits after. Do I round it up or do I hold it? Looks like for this one, the 8 would force the 6 to round up to a 7, so my answer should be 12.7. Last but not least, I have 6 minus 3.0. I have no digits after the decimal. Here I have 1, so I should round my answer so I have no digits after my decimal. So that answer should be a solid 3. Number 12. Consider 3 sets of data that have been recorded after measuring a piece of wood that is exactly 6.000 meters long. So we want to look and figure out which of these data sets, A, B, or C, is the most accurate, and then which data set is the most precise. We have to know the difference between these two. When something is accurate, that means that the true value is reflected in the data as close as possible. We talk about precision. We don't necessarily care about how our data set matches up with the true value, but we care about how close our measurements are together. So what is the level of uncertainty in our measurements? So if we look at letter A, which set is the most accurate, we want to find the one that is closest to 6. This value here looks like it's off by about 0.2. So that's a pretty significant difference when we have this much precision. In this case, it's off by 0.002, 0.004, and 0.003, so that's very close. And if you look at set C, this set is also very similar to that. So if I had to report a level of precision, or which one's the most accurate, that would be set B. Because again, we're looking at 6.00, that's only off by 0.002, 0.004, and 0.003. Whereas all of these are off by the 0.2 or 0.1 type thing. So these are much more off than this one here. With regards to precision, we want to look at how the values vary from each other. So if we look at set A, this value ranges from 0.064 or 0.864, 0.878, 0.871. They vary in about 0.014, so that's a pretty big variation with regards to what our precision is. If we look at this here, they only vary by 0.002, which is very, very precise. Here, they vary by about 0.004. So this has a greater variation, even though it's very close, has a greater variation than set B. So set B is going to be more precise. Number 13, convert the following quantities from one unit to another using the following equivalent statements. Now the equivalent statements aren't listed here because I couldn't fit them in the slide, but you see them on the packet. You must show the setup with dimensional analysis, no exceptions. Dimensional analysis is an excellent and very useful stepwise procedure to solving a lot of chemistry problems, and I really encourage you to get the habits down for using this routinely now so your life becomes a lot easier moving forward. So we need to convert from 30 meters to miles. If I look at my conversions, I find that I want to multiply by the conversion factor where meters is on bottom, yards is on top, but I have to convert it to miles, so then I'm going to put yards on bottom, miles on top. I'm going to do 30 times 1.094 divided by 1760, and when you round it for significant digits, it should be 0.002 miles. I have one sig fig, I have one sig fig. Moving on to letter B, there's the setup for that. I want to go yards to miles. I would just need to use this final conversion that I used previously. So I'm going to take 1500 divided by 1760, and I get 0.85 miles. Again, 2 sig figs in my question, 2 sig figs in my answer. Letter C, 206 miles to meters. So it's going to basically be very similar to this one up here, but it's going to be flipped. So you'll notice the conversion factors might be flipped a little bit. So I have 206 miles. For every 1 mile, that's 1,760 yards. So I'm going to multiply that. And then I'm going to divide that by 1.094. And with 3 sig figs rounded, you should get 331,000 meters. Kilograms to pounds is a little bit simpler because it's only one step. So I'm going to start with 34 kilograms on the left. I'm going to multiply it in a way that kilograms cancel. So I'm going to take 34 times 2.205, and that will give me 75 pounds. Again, rounded to 2 sig figs. Same thing here, except the units are flipped. So I'm going to have 34 pounds. I'm going to divide it this time by 2.205, and you'll find that your answer is 15 kilograms. Number 14, we want to select the larger quantity below. Use dimensional analysis to support your claim and equivalent statements from question 13. So the only way we can really compare these two measurements is by converting them to a like measurement. So I would have to either convert 3 miles to meters and then compare what those two are, or convert my 3,000 meters to miles and then again compare to how those two numbers shape out. So let's go through one of these. I chose to select 3,000 meters to miles. So if you look at 3,000 meters, I'm going to cancel out meters, and that will give me yards. So I'm going to take 3,000 times 1.094. And then to convert it from yards to miles, I need to divide by 1760 yards. So that way yards cancel here and here. And then I'm left with miles. When I do this and I plug it into my calculator and I round for significant digits, I start with 4 digits in my problem. I want to end with 4. That'll be 1.865 miles. So if I compare 3 miles to 1.865 miles, which is going to be larger? 3 miles or 3,000 meters? Well, looks like it's going to be 3 miles, because again, 3 miles exceeds the 1.865 when we convert meters to miles. Same thing with letter B. I have to determine which is greater, 10 kilograms or 25 pounds. So choose one, whichever one you prefer, and convert it to a like unit and then compare. So I chose to go from pounds to kilograms. So I'm going to take 25 pounds divided by 2.205 pounds to kilograms. I get 11 kilograms. And again, I rounded that to 2 sig figs because I have 2 sig figs here. So which is greater, 10 kilograms or 11 kilograms? Well, 11 kilograms is going to be larger, so that indicates to me that 25 pounds would be the larger unit. 15. We're going to convert the following temperatures from one unit to another. So in order to do this, you have to know your conversion from Celsius to Kelvin. A Kelvin temperature is equal to the Celsius temperature plus 273. That's basically your constant that's going to allow it. So if I plug 13 Kelvin in for my temperature in Kelvin, I find that I'm basically solving for a single variable, which is an algebra principle. I'll subtract 273 from both sides, and I'll find that my temperature in Celsius is negative 260 degrees Celsius. Same thing is what I'm going to do here for the next one. I have 1390 degrees Celsius, and I want to convert that to Kelvin. So again, set up my formula, plug in my Celsius there, add it to 273, and my temperature in Kelvin is 1663 Kelvin. Number 16. When discussing a change in temperature, why will it not matter if the change is recorded in Celsius or Kelvin? Use an example to support your claim. Well, let's suppose we were going from 10 degrees Celsius to 20 degrees Celsius. That is just the same as going from 283 Kelvin to 293 Kelvin. Here we have a difference in 10 degrees Celsius. Here we have a difference in 10 degree Kelvin. And if we were to convert these to like units, you'll find that 10 degrees Celsius is equal to 283 Kelvin, and 20 degrees Celsius is equal to 293 Kelvin. So both examples show that the change in temperature, or delta T, oftentimes in this class you'll see change being referred to as the Greek delta. That's the value of 10. When observing the change, 1 degree Celsius is equivalent to 1 Kelvin. Even if the temperature is in Celsius and it's negative, we want to observe the absolute change to relate it to Kelvin. So remember, Kelvin is an absolute scale, so you can't have anything below absolute 0 or 0 Kelvin. So you'll notice that Celsius can go into the negative, but Kelvin cannot. Even though you have negatives, and if you were to basically compare the change, you might have a negative value and things like that, again, it really doesn't matter all that much. We want to find the absolute change. The magnitude of going from 10 to 11, 11 to 12 is the same thing as going from 283 to 284 to 285. Okay. Moving on. Number 17. Here we have 3 different beakers, which have different degrees of precision, and we want to answer the following questions. We want to label the amount of water in each of the 3 beakers to the correct number of significant digits. So when you're taking measurements, we have to remember we want to go as accurate as the instrument will let us, plus an estimated digit. So in this case, we're between 32 and 33. I'm certain it's greater than 32, and I'm certain it's less than 33. So I'm going to give an estimate here of about 32.7 milliliters. Now I know that none of these here have any unit markings. Most often in chemistry courses, we're going to use milliliter to measure most volumes in our labs. And most of the markings on graduated cylinders are labeled in milliliters. If we look at the next one, it goes from 30 to 40 to 50. Well, I'm certain that it's greater than 30, but I don't know the certainty with regards to the ones place. So I have to make an estimate for this ones place here. So for me, I would say that's 32, maybe 33 milliliters. Again, you could report 32 milliliters here, and that would be an acceptable answer. Just like for this one here, if you put 32.6 or 32.8 or anywhere that's in an acceptable range there, that's fine. You just didn't want to put, like 32.75. That would be too precise for the instrument we have. How about this last one? I'm certain it's greater than 32.7, but less than 32.8. So I have to estimate my hundredths place. So I'm going to go ahead and say 32.72. That sounds like that's a pretty good estimate. Okay, letter B. Is it possible for each of the 3 beakers to contain this exact same amount of water? If no, why not? If yes, did you report the volumes as the same in part A? Explain. So there's a little bit of leniency with how you could have answered this question, because you have to basically state the claim that yes, they are the exact same, or no, they're not, and then that led to the follow-up. So I'll go ahead and share with you what I interpreted. So I'm going to go ahead and say yes, all the volumes could be identical to each other, because the more precise volume readings can be rounded to the other volume readings. Because again, we're dealing with different graduated markings here. So there's some level of uncertainty where I could be uncertain in this measurement, but maybe I'm more certain in this measurement. So there's a different varying level of certainty. But because the volumes are in 3 different measuring devices, each with its own unique uncertainty, we cannot say with certainty that all 3 beakers contain the same amount of water. So again, even though it looks like they could be the same, we don't know for sure, because it is 3 separate beakers that have different, ability to measure, so we can't be 100% sure. Letter C. Suppose you pour the water from these 3 beakers into one container. What should be the volume in the container reported to the correct number of significant figures? So to answer this question, and your answer might be different than mine based on your measurements for letter A, you want to add these 3 together, and then that will give you your answer. Now remember, when you add things, you have to follow significant figure rules. So if I look at my measurement here, my least specific measurement is this middle one here, because you could have put 32, maybe you put 33. There's nothing after the decimal. So when I add these up, I want to make sure I round it so nothing comes after the decimal. When I add it up, I find that my answer here is 98.43, but again, I want to round it to significant figures, and that would just be 98 milliliters. 18. How many microliters are there in 5.5 milliliters? Oh, looks like I interpreted it differently. So I did the flip side of this. I will post a correct solution in the video description. Here I have 5.5 microliters. I converted from microliters to liters, and then I converted from liters to milliliters. Now, of course, I did the reverse of this, so your answer is going to be different. I'm going to take 5.5 microliters. I'm going to divide it by 1 million microliters, because there's 1 million microliters in 1 liter. And then for every 1 liter, there's 1,000 milliliters. So if you do that math, you should get 5.5 times 10 to the negative third. Okay? Now, if we were to go the other way with this, I can kind of do this really quickly. I have 5.5 milliliters here. I'm going to essentially convert that to liters. So I would divide by 1,000, and then I would multiply by 1,000,000. So if I look at how zeros cancel, I'm essentially multiplying this by 1,000. So the correct answer, if you did it the right way, should be 5.5 times 10 to the third milliliters. So this would be for the way that I interpret it, which was wrong. The answer should be 5.5 times 10 to the third milliliters. Or microliters. There we go. Okay, now on to 19. Match each description below with the following particle diagrams. A particle diagram may be used more than once or not used at all. In AP Chemistry, College Board likes to show lots of particle diagrams, so it's important for you to get practice and familiarity with how to interpret these as practice. So let's find one that's a gaseous compound. So the only one that's a true gaseous compound would be letter 4. A compound, again, contains different types of elements. So here I have a different element with a different element, a different element with a different element, and a different element with a different element. And I know it's gaseous due to the spacing. These are very well spaced out. They're not in tight together, which would indicate a solid, or tight together but not orderly like a liquid. So number 4 would be the best answer. Now, 2 and 3 also contain a gaseous compound, but they both also have a gaseous element present. So it's not a pure gaseous compound. We would say it's a gaseous, essentially mixture. So if you look here at 2 and 3, I have a gas compound here, and I have a gas compound here. But I also have, a molecule here that is diatomic, and then here I have just a single element as well that's also a gas. So these would not be just a gaseous compound, they would be mixtures. How about this one? B, a mixture of 2 gaseous elements. Well, the only one that's true for gaseous elements would be 6, because if you look here, I have a single element, 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 a single element. Again, that's what we would look for here. Okay. there's two elements, and they're a mixture. The solid, that would only be letter 5, because these are the only ones where they're nice and neatly arranged in an orderly pattern, and it's an element because it's just a single type of atom that we see there. Letter D is a mixture of a gaseous element and a gaseous compound. We could say, like I showed earlier, that 2 and 3 are this, because again, we have a gaseous element. In this case, it would be that single atom there. In this case, it would be the diatomic molecule, which in this case would be an element as well. And then we have the compound as well. Number 20, it says a material will float on the surface of a liquid if the material has a density less than that of a liquid. Given that the density of water is approximately 1 gram per milliliter, will a block of material having a volume of 1.2 times 10 to the 4th cubic inches and weighing 350 pounds float or sink when placed in a reservoir of water? So what we have to do is we have to figure out what the density of this particular block is and then compare that density to the density of water. So there's a couple of choices here. I could solve for the density of this object in pounds per cubic inches, and then I could compare that to the density of water in pounds per cubic inches, or I could convert pounds to grams. I can convert cubic inches to milliliters, then find the density in grams per milliliters, and then compare it to that of water. So I'm going to go ahead and do that second path that I described. So let's start off with 350 pounds. I'm going to use some of those conversion factors that I showed in number 13 earlier. So I know that for every 1 kilogram, that's 2.205 pounds. So I would divide that to give me my kilogram mass, but I want it in grams. I know that for every 1 kilogram, that's 1,000 grams. So when I do my math, I find that the mass of this particular block is 1.6 times 10 to the 5th grams. Next, let's convert the space it takes up, or the volume, to milliliters. That way I can solve for the density. So cubic inches, I know there's 2.54 centimeters in every inch. However, when dealing with a cubic unit, you have to cube the units, and then as a result, cube the numbers. So ordinarily, it'd be 2.54 centimeters for every 1 inch. But since I'm dealing with cubic units, I have to also cube the number as well when I cube that unit. So 1 cubed is 1, so that doesn't affect the division part of this. But when I cube 2.54, that's going to affect my answer. So I'm going to take 1.2 times 10 to the 4th times 2.54 cubed. That would give me my volume in cubic centimeters. But again, I want milliliters. Luckily, cubic centimeters to milliliters is a 1-to-1 ratio. So the answer is the same. When I do that, I get 2.0 times 10 to the 5th milliliters. Now that I have my grams in my mass, and I have my volume in milliliters, let's solve for density. Density is equal to your mass divided by your volume. So if I take 1.6 times 10 to the 5th divided by 2.0 times 10 to the 5th, I get 0.80. Now remember, a material will float on the surface of a liquid if the material has a density less than that of the liquid. So since I'm comparing the density of the block to the density here of the water, how does 0.8 compare to 1? Well, 0.8 is less than 1. So will this object float or will it sink? It's going to float because it's less. 21. We're given a couple of isotopic symbols here, and we want to determine the number of protons, electrons, and neutrons. Here we have lead 210. So protons for lead, that's the identity of lead. You get that from the atomic number here at the bottom. That's 82. Now there's no charge indication here in the upper right hand corner, so we're going to assume this is a neutral atom. So the number of protons and electrons should be the same. If I wanted to solve for neutrons, I'm going to take the mass number, which is protons and neutrons combined, 210, and I'm going to subtract 82 from that. So 210 minus 82, it's going to give me 128. And then again, electrons are equal to protons because they don't give us any information regarding charge. Sulfur 34, if an isotope is written out like this, it's telling you the name of the element and the mass number. Now, in order to figure out protons, we would have to reference a periodic table because there's no indication of atomic number listed here. So if I check my periodic table, the protons are 16. Again, to solve for neutrons, that's your mass number minus your atomic number. So 34 minus 16 would be 18 neutrons. And then, again, there's no information about charge here. They don't tell us if it's an ion or not. So we're going to assume the protons are equal to the electrons, and that would be 16 as well. 22. Use the attached periodic table, which I gave you, to determine how many elements within the first 20 have atoms with A, the same number of protons and electrons, and B, the same number of protons and neutrons. Well, looking at the periodic table I gave you, that's a regular standard periodic table which lists how different atoms compare. There's no charge information at all. So all 20 of those first elements are going to have the same number of protons and electrons. The periodic table, again, represents neutral atoms. You would need charge data to answer this, which the periodic table does not provide. Letter B, which ones have the same number of protons and neutrons? This one's a little bit trickier because the periodic table I gave you has average atomic masses, so you'd have to make an assumption based on their abundance. So you might have to do some rounding. So if you looked at the first 20 elements, 9 of them would have the same number of protons and neutrons. And those 9 are helium, carbon, nitrogen, oxygen, neon, magnesium, silicon, sulfur, and calcium. Now, how do you come up with those? You want to look at your mass number, and which is, again, they don't give you an exact mass number, they give you the average mass number, so you'd have to round it to the nearest whole number, and then you'd want to divide it by 2, which would then basically tell you that half of that mass number is protons and half of that mass number is neutrons. Now again, most of these numbers are pretty close to one number or the other. Like for example with carbon, it's 12.01, right? 12.01 you can effectively round to 12 because most carbon in the world that exists is carbon-12. So when you take your mass number divided by 2, you get your atomic number, which again, your new protons would have to equal your neutrons for this to be correct. All right, let's go ahead and talk about some nomenclature. Let's write the formula for the following molecular compounds. We're given dinitrogen tetroxide, so you have to know your prefixes here. Di is 2, tetra is 4, so it's N2O4. Phosphorus pentachloride, they don't give us a prefix for phosphorus, so that's 1P. Pentachloride is 5 chlorines, so PCl5 would be the answer there. Iodine trifluoride, again, 1 iodine, 3 fluorides, IF3. Nitrogen dioxide, 1 N, 2 O's. Dihydrogen monoxide, 2 H's, 1 O. That's water, H2O. Ammonium nitrate, to answer this, you'd have to know your polyatomic ions. Ammonium is NH4, nitrate is NO3. Ammonium has a charge of +1, nitrate has a charge of -1, so NH4, NO3. I'm going to go through these next ones a little bit faster to save some time. Copper 2 bromide, again that's Cu2+, Br-. You have to have 2 Br- to give you 1 Cu2+, so that's CuBr2. The difference between this one and this one is the charge in copper here is +1, so Br-, Cu+, it would just be CuBr. Zinc hydrogen sulfate, again, you have to know that zinc is Zn2+, and hydrogen sulfate is HSO4-, so you'd have to put zinc HSO4, put that in parentheses because it's polyatomic, and put a little 2 on the outside. Aluminum sulfate, that's Al, 3+, SO4, 2-, so you have to have 2 aluminums for every 3 sulfates, because again, if you have 6+ overall here, and 6- here for that to work. Sodium perchlorate, sodium is Na+, perchlorate is ClO4-, so it's going to be a 1-to-1 ratio. NaClO4 works great. Copper 2 iodite, you have to know that copper is Cu2+, and iodite is IO2-, so you have to have 2 of the minuses to equal the 2+, so that's CuIO2, in parentheses the little 2. Let's do the reverse. These are a little bit faster. Let's convert the following formulae to names. N2O5, got to know your prefixes. Dinitrogen pentoxide. You don't want to put pentaoxide. You don't want to have that AO vowel combo. PCl3, that's phosphorus trichloride. SF6, that's sulfur hexafluoride. Again, there's only one S, so it's sulfur hexafluoride 6F. H2O, that's dihydrogen monoxide, which we know is water. Cl2O, that's dichlorine monoxide, 2 chlorines, 1 oxygen. Remember, you always want to use a prefix for a molecular compound where your second one, always, so even if it's 1, you want to put a prefix. Your first element in a molecular compound, you only want to put a prefix if it's 2 or more. So let's go NaNO3. This one's ionic in nature, so we have to name it how we see it. That's sodium, and then NO3 is nitrate, so sodium nitrate. KMNO4, That's potassium permanganate. You're not going to use prefixes here unless the polyatomic has a prefix. CaC2O4, so that's oxalate, so I have calcium oxalate. CuSO4, I have copper, but copper is unique because it's polyvalent, which means it can have multiple charges, which means it has a Roman numeral. So I have to figure that out. SO4 is 2 minus inherently, so if I only have one copper, the copper has to be a 2 plus. So it would be copper 2 sulfate. Here I have a similar deal, but I have Cu with a little 2 down here, and then I have SO4. So SO4, as I just said, is 2 minus. I have 2 coppers to balance out that 1, 2 minus, which means that each of these coppers have to have a Roman numeral of 1, or a charge of +1. So it's copper 1 sulfate. Last but not least, I have KNO2. I know that K here is potassium, and I know that NO2 is not nitrate, which is up here, but it's rather nitrite. It has 1 less oxygen, so it's nitrite. So here I have potassium nitrite. Lastly, I have LiClO4. Li is lithium, ClO4 is perchlorate, so here I have lithium perchlorate. Thanks for tuning into the video. See you in class.